Okay, let's continue our discussion. Of course, this expression V sub O in terms of D, which depends on the location of the column with respect to the plan of the math foundation, can be obtained from the figure presented above. So this one, for this one, this is a formula, of course, that you are familiar with in your reinforced concrete design. So for step 7, from the moment diagram of all strips in one direction, either x or y, obtain the maximum positive and negative moments per unit width. And the last one is you have to determine the area of the steel per unit width for positive and negative reinforcement in the x and y direction. So using our factored moment equation. So for factored moment formula, this is P is of S Fy times B minus A divided by A is the area of the steel using this equation. So let's have the application for the structural design for a math foundation. Of course, you are given with a plan of a math foundation. There are 12 columns in this concrete slab, and they are given with the dead load and live load per column. Of course, the column section is 24 inches by 24 inches, and the size of the mat foundation is 76 by 9650. So this is the plan of a mat foundation. So you just have to follow the figure of the steps that was presented a while ago. So the first thing is you have to verify that the soil pressure are less than the net allowable bearing capacity. So the given net allowable bearing capacity pressure is 1.5 kips per square feet. So you're going to solve for the soil pressure for each column, and it should be less than the net allowable bearing capacity. So before anything else, we have to compute for the service load. So we can compute for the service load. You have to compute first for the column dead load and the column live load. The total column dead load is 3,550 kips, and the total column live load is 2,230 kips. So we just sum up our load per column for the dead load and the live load. And we can compute now for our service load. Sum up our column dead load and the column live load. We are given with 5,780 kips. Then, of course, we can compute now for our factored load, which is 1.4 of the dead load plus 1.7 of the live load. And that is equivalent to 8,761 kips. So the moment of inertia of the foundation are, you have your moment of inertia along the x direction is equal to 5,603 times 10 to the third feet to the fourth, and your moment of inertia along the y-axis is 3,512 times 10 cubed. And of course, you have to compute for I sub x. You have to compute for x prime and y prime. So since our service load, which is our total column load, is 5,780, multiply that to x prime, and that would be equivalent to the column load multiplied to the distance from the center of the column load towards the reference point. So for this example, this is our reference point. So meaning to say, if it's our reference point, so the total column load times x prime is equal to the column load. So you just have to add this column load multiplied from the center of this column load towards the reference point. You have to add all of this column load multiplied to each distance to the reference point, and along x direction if you're going to compute for, meaning to say, if you're going to compute for x prime, our distance is along x direction towards the reference point. So meaning to say for this, you will have your x prime is equal to 36.66 feet. And since we have computed for x prime, we can compute now for our e sub x. Our e sub x now is, we simply have to subtract, this is 36.66 feet minus b all over 2. Width is 70. We are given with the width which is 76 all over 2. So you can have now given for the eccentricity along x direction is 0.664 feet. So this is now our e sub x, eccentricity along x direction. To compute now for the eccentricity along y direction, you have to compute for y prime. So we have the summation m sub x equal to 0. So still, you have the reference point. This is our reference point. And the column, the service load or the total column load times y prime is equal to the column load multiplied to each distance from the center of the column load towards the reference point along y direction. So this is along y direction so that you can compute for y prime. So you just have to review your statics. So if you're going to have, sum up our each of the column load multiplied to, this is a column load, multiplied to its distance from the center towards the reference point. And we can compute now for y prime, which is equivalent to 44.273 feet. And basically, our eccentricity along y direction now is equal to 44.723 subtracted by, this is 90 all over 2, 96 all over 2, so we get negative 0.727. So meaning to say our e sub y is below the centroid of the foundation, of the mat foundation. So this is our e sub y. So if we're going to compute now for the moment caused by eccentricity, so the moment caused by eccentricity, so for this one, so this is actually, if we're going to have the location for, this is the centroid of our mat foundation. So from the mat foundation, this is our location of our e sub x, and this is the location for our e sub y. So this is y, this is x, so this is e sub x, and this is our e sub y. So positive e sub x and negative e sub y. So from there, you can compute now for m sub x, which is q multiplied to e sub y, and that is equal to 6,369 feet, and m sub y, q times e sub x, and that is equal to 5,817 feet. So for this one, we are now given with our moment caused by eccentricity along x direction and y direction. So basically, since we have now the value of the parameters q, a, you have your m sub y, you have the x, I sub y, and we have now the value for m sub x and y and I sub x. X here is our x prime, our y is our y prime. So for this one, we can have now the values for, you simply have to substitute to our equation the values. Basically for x, this is the distance for each of the column load towards the centroid, so along x direction. This one is the y is the distance of our column load, of our column rather, from the centroid of the column towards the eccentricity. So along y direction, this is from the centroid of the column towards the eccentricity, towards the center of the mat foundation. So meaning to say, this is the center of the mat foundation. Since we have computed now our eccentricity, this is the centroid. So for x and y, that is from the column, the centroid of the column towards the distance towards this centroid of the column, that is our along x direction, and for that is for x. For y, that is from the centroid of the column towards the centroid of the mat foundation along y direction. So that is for our y and x in our equation here. So you simply have to substitute some of the variables, then you try to simplify. When you simplify this one, this is now our working equation. So we have our working equation. This is the simplified form after we have substituted the values of the parameters. Of course, we have the presence of our x and our y, so that we can have a organized tabulation, organized value for our soil pressure for each point, for each column. So let us tabulate this one. You simply have to identify our Q over A. You have your x, you have your y. Then you multiply your x times the our 0.0017. You obtain this one. This one, Q over A, of course, this is the value all throughout for our column. For our x, as mentioned a while ago, as discussed, that is the distance from the column centroid towards the centroid of the mat foundation along x direction. Then you multiply that one to 0.0017, you have this expression. Then our y is the distance from the centroid of the column along towards the center of the mat foundation along y direction. Then you multiply that one to 0.0011, you have this equation. So basically, if we try to simplify this expression, you can have the value for Q, for the soil pressure for each column, you are having this numerical value. And if you're going to observe all of this value, all of this soil pressure are less than the given value for the net allowable soil bearing capacity, which is 1.5 kips per square feet. So that is for this given problem.